So the term logarithm, I love highlighting stuff. I feel like using the green highlighter today, is used to describe the inverse of a power. So if you have 10 to the x, you'd have a log of base 10. If you have 2 to the x, we saw we'd have a log of base 2. Uh-oh. So here's the graph of 10 to the x, and we flip it over the line y equals x to get the inverse, and that inverse is log base 10 to the x. And so the question was, what does the button on your calculator that just says log? That's always a base 10. So log base 10 of x is called the common logarithm, and you don't have to write the 10. That's why there's a 10x in the second function of it. So you go to your calculator and say, for example, here is an easy question. 10 to the x equals 100. You know the answer is 2. But if you took log base 10 of both sides, and you don't have to write that 10, then your calculator should tell you that it's 2. So going to your calculator, you've got the log button right beside the 7. So if you go log of 100, it's asking you 10 to what exponent would be 100? It should be 2.
So why don't we just like this fancy thing instead of like finding bases and stuff?
When we can't find the bases to be the same, then we're going to need to use this. Right? When we can find the bases to be the same, we can use the technique we were using before, but often we can't. Yes? Yes, if you have the TI-83, it doesn't have the log base. What do you do? So, for example, right, for those of you that have the log base, you can do log base 2 of 7 and get an answer, right? For those of you that don't, type in log 7 divided by log 2. And we'll find out why that works later. So this is equal to that. In fact, we can change any log to be a common log if we want. So here's our definition of a logarithm. And logarithms are connected to exponential functions. So I'd like you to write this at the bottom. The exponential form is some base to the power of, or to the exponent of x is equal to y. In the logarithmic form, the base is there. Log solve for exponents, so the x value will now be on the right-hand side of your equation. And y would be on the left. Logarithmic form. Now, technically, the way that you get from the exponential form to the logarithmic form, if you had the exponential form, so I'll write it here, b to the x equals y, and you took log base b of both sides, well, the log base b and the b to the x would cancel each other out, and this side would just be x. And you'd get x equals log base b of y. However, with logarithms, it tends to be that people just know the definition of it, don't show this work in between, and say, I know this is my base of my exponential function, and the base goes there. I know that my exponent is what a logarithm is equal to. And I know that my answer in my exponential function is what is inside my logarithm. And so we get to the point where we sort of see one and think of the other one, and vice versa. So a lot of times that we see the logarithm, because the logarithm is new. Exponents you're pretty comfortable with, right? In grade 9, exponents were hard. What? We're writing tiny numbers? What's this new math? Okay? So what we're going to do with logarithms is you're going to read this as log base b of y equals x, but you'll probably always think exponentially. And so when I see this, there's my base. I'm going to think b to what exponent is equal to y? Ooh, I'll change the x to green too. That's sort of how I visualize a logarithm. I say the base is b. What exponent would make it equal to y? That's the answer to it. Because that is b to the x equals y is the exponential form. So we start off in example 1. Was there a question? Start off in example 1 with just practicing changing from one form to another. These are true statements. 3 cubed is 27, right? So in log form, we would say log, the base is 3, the answer is 27, is equal to 3. I, 5 to the negative 2 is equal to 1 over 25. I would write log of base 5, 1 over 25 is equal to negative 2. And in part 3, 4 to the 0 is equal to 1. So log of base 4 of 1 is equal to 0. Logs always solve for exponents. So if I color code these, when I'm looking at the logarithms, I'm really thinking 3 to what exponent would be 27? It would be 3. 5 to what exponent is equal to 1 over 25? That would be negative 2. And 4 to what exponent is equal to 1? That would be 0. And I find if I think of logarithms that way, then they start to make sense. And what you're really doing is just applying the definition back and forth. So whenever you have a logarithm, you can change it to exponential form if that helps you think about it better. Whenever you have, not very many people have exponential form and go, oh, this would be so much easier if I thought about it as a logarithm. That doesn't usually happen, but you could if you wanted to. Anytime you have exponential form, change it to logarithmic form. So look at part B and just read each logarithm and say to yourself, does the answer make sense? Log 7 of 49, does that make sense that that's 2? Log 4 of 1 over 64, does it make sense that it's negative 3? And the reason that you're making sense of it is because in your head, you're doing exactly what we did here. You're changing it to exponential form, which you're more comfortable with. What's the base of part I? It's 7. What's the exponent is 2? The answer is 49. In 2, it says 4 to what exponent? Negative 3 is equal to 1 over 64. And part 3, 10 to the negative 4 is equal to 1 over 10,000. So practice the definition on these questions 5, 6, and 8.